Project presentation of Group 23, Artificial Heart. Heart, one of the most essential organs of a human being, has long been identified as the center of the entire body, the seat of life. It deserves our attention. Heart is a blood pump. It's a breathing design with 4 chambers, 2 upper atria and 2 lower ventricles. The upper ones receive blood, while the lower ones discharge. Valves between atria and ventricles are used to prevent blood from flowing backward. Heartbeat, including systole and diastole, is performed regularly and constantly. As a result, oxygen is transformed and available for all parts of the body through the circulation. However, heart can become faulty, and if the fault is something like your left ventricle decides to begin a streak, you have to prepare for all bad luck. Heart failure faces you with not only the sufferings from disabilities in cardiac function, but also extremely scarce heart transplant donors. With worse survival rate than many cancers, time is life. Waiting means death. Let's have a look at what really happens to our society. In modern days, heart attack has been one of the greatest killers of human beings. According to a GBD study, about 15.9 million myocardial infarctions occurring in 2015 worldwide. More than 400,000 people a year die of heart disease, and more than 3,000 are waiting for heart transplants. Unfortunately, the number is now increasing. So we discussed, investigated, and finally made a decision. A new artificial heart is what we are looking for. Actually, pre-existing models usually have some common disadvantages: cumbersome, difficult to work for a long time, and triggering immune responses. As shown in the graph, the survival percent of device implant went down to a relatively low number as time passed. We want to use our design to change this condition. Advanced drive device, wireless charging, Bluetooth monitoring, innovative material, market adaptability combine to form our model. This is the assumed 3D palm image. We use 2 chambers instead of 4 to complete the 2 circulations in our body. With the impellers rotate on their axis, blood is driven. Battery and receiver are built connected to the shaft inside the machine.
Speaking of energy and charging, our group thinks that the inductive charging may be the best way to charge our artificial heart. Inductive charging uses an electromagnetic field to transfer energy between 2 objects through electromagnetic induction. This is usually done with a charging station. Energy is sent through an inductive coupling to an electrical device, which can then use the energy to charge batteries or run the devices. If we simplify it, it will be something like this. Induction chargers use an induction coil to create an alternating electromagnetic field from within a charging base, and the second induction coil in the probable device takes power from the electromagnetic field and converts it back into electric current to charge the battery. We are going to put 2 coils, one inside our body, one outside our body. If we give electrical current to one coil, then it will create an alternating electromagnetic field, and then there will be current in another coils which is inside our body. Then we can charge the battery inside our body. We are going to use 2 different types of batteries. The bigger one is going to generate power in daily life, but when it is run out of energy, the smaller one will be in use. Speaking of advantage of inductive charging, I think there are 3 main aspects. The first one, it has protected connections. No corrosion when the electronics are all enclosed, away from water or oxygen in the atmosphere. Less risk of electrical faults, such as short circuit due to insulation failure, especially when connections are made or broken frequently. The second one is it has low infection risks. For embedded medical devices, transmission of power via a magnetic field passing through the skin avoids the infection risks associated with wires penetrating the skin. With two isolated batteries, under no circumstances will the heart run out of energy, so it can beat continuously.
As we all know, monitoring system plays a vital role in implant organ. As we conclude, now all the system could be divided to two areas, wired system and wireless system. Now, let me introduce wireless system first. As you can see in the PowerPoint, it's a normal wireless system. It adopts the electromagnetic transmitting way. As you can see, it's a wireless energy transfer system. Frankly speaking, it's stable, but it's quite hard to control the area of electromagnetics, so it could cause interference. Therefore, a new transcutaneous communication system was created. You can see it is connected with Earth ground and external monitor and back to the artificial heart or artificial organ. Here it has a communication unit. It's quite good, but because of internal wires, maybe it could lead to infection. So we refuse these two ways. Dun, dun, dun. We adopt a more powerful design, Bluetooth radio wave technology. It's cool, isn't it? Now let's imagine it. It could connect with your laptop, phone, or even Apple Watch. You can clearly get your heart curve, which includes pressure, flow rate, just like scoping the reservoir, more securely. If the data which received and processed by black box has errors, your family and the hospital nearby will receive a message at once. Simultaneously, your artificial heart will get a first aid by an electric shock. It's very powerful, isn't it? Okay, let's see the format. First of all, let's see the security area. As I just seen, our way is more safer than these two ways. For cost, just for example, the cost of Bluetooth chip is under $3. Oh my god, it's very cheaper. I can't compare with these two expensive ways. And for consumption of energy, the Bluetooth is very efficiency, so the consumption of energy is very low. And what about available distance? Our Bluetooth radio wave can transmit at least 3 meters. So compare with these two, we also take advantage. Above all, so what's the best design? Done. Of course, it's our Bluetooth radio wave.
Now we are going to discuss the materials of the artificial heart. There are lots of prerequisites to build an artificial heart, and one of them is that the materials are supposed to be suitable. The materials should be biocompatible, non-toxic, and biodurable. Their structure and hardness should correspond to their function. The main part of an artificial heart is the pump, which provides blood transportation. Blood is a kind of electrolyte containing a large content of ions. There are some oxygen and other oxidants in it too. The inner part of the pump and the vessel will contact the blood, so it is very easy for them to be oxidized. After an artificial heart is implanted into a patient's body, the immune response will occur and sometimes will cause inflammation. So, we are supposed to choose materials which will cause less immune response. Price is another factor that we must consider. With the development of the technology in polymer, more suitable and inexpensive materials has appeared in the market. In this project, we searched 3 kinds of materials. There are polyurethane elastomer, silicon rubber, and titanium alloy. The first one is polyurethane elastomer. It consists of mainly 3 parts: the backbone, the diisocyanate, and the chain extender. And the structure leads to many of its advantages. The polyurethane has a good biocompatibility, flexural endurance, high strength, and relevant technologies have become mature in applications. We mainly find 5 types of polyurethane elastomers, among which we decided to use 2 ones colored in red. Biostable polyurethane is a good material to build blood vessels, and we'll use polyurethane coating to cover the parts exposed to blood. The second one is a silicon rubber. The silicon rubber is a kind of polymer which is made of silicon monomers. A silicon monomer is made from silicon and methane chloride. The silicon rubber is flexible and can be changed into various forms and shapes. It has a high biocompatibility and biodurability which allow it to stay inside the body for at least 2 years. It's non-toxic and non-allergic. It can also repel water and form wood-like shapes. The silicon rubber can be sterilized easily, so it can reduce the chance of infection. Although there will be some immune response after implantation, we can use some drugs to weaken the reaction. The third one is titanium alloy. The titanium alloy has the highest strength to density ratio in metals and can resist corrosion in seawater and chlorine. As a result, titanium will not be easily oxidized when contacting the blood. Titanium alloy has a low density but a high intensity. It will not cause obvious immune response. So, titanium is one of the most suitable materials to make artificial organs. Here are the prices of each material. Polyurethane elastomer is $4.5 per kilogram. Silicon rubber is $16.7 per kilogram. Titanium alloy is $2.3 per kilogram. After we compared these 3 kinds of materials, we found that the titanium is the most suitable material for building the pump, but it's not flexible enough to use the titanium to make the vessels. So, we want to use titanium alloy to make the main part, including the pump of the artificial heart, using polyurethane elastomer coating to cover its surface. And we'll use the mixture of silicon and polyurethane elastomer to build the vessel.
To calculate the total power, we know that a normal adult's heart transforms 60 to 80 milliliters blood per heartbeat, assume beating 75 times a minute, 70 milliliters per time, and the average pressure of blood is 16,000 pascal. So the working power of a heart is 1.4 watt. The efficiency of the energy conversion according to water pump is 60%, and the efficiency of the charging system is 80%, so the total power is 2.9 watt. It's quite small.
This is the result of our market research. We find that more than 17.5 billion people are dying every year globally because of heart disease, and many of those lives could have been saved if they were implanted with new hearts. And therefore, this indicates a huge potential market for our new design. This is the calculation of our cost. The first part is material. And this contains purchasing raw materials, processing them, and all kinds of other things like wireless charger and receivers. All of these things cost our money. And although the raw materials are pretty cheap, processing them is kind of expensive. And the charger and receivers are never cheap things. And we have also used many already existing patents, in other words, designs. So there is something called design cost. In total, our cost is $2,010. Compared with its cost, the price is a little bit expensive. However, when compared with other already existing designs, it is definitely cheap.